Picture the flat plane and think of a matrix as a machine. You feed it an arrow and it hands you back another arrow. Feed it a whole fan of arrows and most of them swing 2 points somewhere new. Rotated, stretched, reshuffled. But look carefully. A couple of arrows come back lying on the exact same line they started on, only longer or shorter. Those special directions are what this whole lesson is about. Here is the idea in one line. If a matrix A times some non-zero vector V gives you back just a number lambda times that very same V, then we give them names. The vector V is an eigenvector of A, and lambda, the amount it gets stretched by, is the eigenvalue. The word eigen is German for its own. An eigenvector keeps its own direction. One rule we never break. We cannot be the zero vector, because the origin obeys the equation for every lambda and tells us nothing. The eigenvalue lambda is simply that stretch factor, and how big it is and its sign tell the whole story. Start with an eigenvector v, pinned to its own line. When lambda is bigger than 1, v stretches. Here, twice as long, same direction. When lambda sits between 0 and 1, v shrinks toward the origin. When lambda is negative, v flips to the exact opposite side of the line. And when lambda is 0, v collapses all the way to the origin. So how do we actually find lambda? Start from the definition and pull everything to one side. Subtract lambda v from both sides. Nothing new yet, just tidying up. Now one clever move. Write lambda as lambda times the identity matrix. So both terms are a matrix hitting v, and factor out v. We're left with the matrix, a minus lambda I, sending a non-zero v straight to 0. A matrix can only crush a non-zero vector down to 0 if it is singular. And a matrix is singular exactly when its determinant is 0. That equation has a name, the characteristic equation. Its solutions are every eigenvalue the matrix has. For a 2 by 2 matrix, there is a clean recipe. Take a general A and subtract lambda straight down the diagonal only. Take the determinant of that, the main diagonal product, minus BC, multiply it out, and it collapses into a tidy quadratic in lambda. And those two coefficients are old friends. A plus d is the trace of A AD minus BC is its determinant. So every 2 by 2 characteristic equation reads the same way. Lambda squared minus trace times lambda plus determinant equals 0, which hands you two instant checks. The eigenvalues always add up to the trace and multiply to the determinant. Let's make it real. Here is a concrete matrix. Trace is 3 plus 4, 7. Determinant is 12 minus 2, 10. So the characteristic equation is lambda squared minus 7 lambda plus 10. That factors cleanly, giving two eigenvalues, 5 and 2. Quick check. They add to 7 and multiply to 10. Both correct. Now the eigenvectors. Start with lambda equals 5 and build a minus 5i. Subtract 5 straight down the diagonal. That matrix times v equals 0 collapses to a single honest equation. Minus 2x plus 2y is 0. So x equals y. Every arrow on the line 1, 1. Pick the cleanest, v1 equals 1, 1. Never trust it. Verify it. A times 1, 1 gives 5, 5, which is exactly 5 times 1, 1. It checks out. For lambda equals 2, the very same routine. A minus 2i has two identical rows, so x plus 2y is 0, and the direction is minus 2, 1. Now put both eigenvectors on the plane. Gold along 1, 1, rows along minus 2, 1. And here is the payoff. Apply A, and neither arrow turns a single degree. The gold one stretches 5 times, the rose one 2 times, each glued to its own line. That is exactly what makes these directions special. Before the tricky cases, a gift that symmetric matrices quietly hand you. This S equals its own transpose, flip it across the diagonal and nothing changes. Its two eigenvectors come out along 1, 1 and 1, minus 1, the gold and rose arrows. And look closely. They meet at a perfect right angle. That is no accident. Every symmetric matrix has eigenvectors that are mutually perpendicular. It's the quiet fact sitting underneath principal component analysis, and a great deal more. Two cases worth meeting. First, a repeated root. This triangular matrix carries its eigenvalues right on the diagonal. Lambda equals 4 twice over. You'd expect two eigenvectors. But solving leaves only one direction. 1, 0. The root repeats, yet the matrix hands back a single eigenvector. We call such a matrix defective. Second case, a pure rotation. This matrix spins every arrow by 90 degrees. Spin it, and no direction survives. Every arrow lands somewhere brand new. So there is no real eigenvector at all. The characteristic equation proves it. Lambda squared plus 1 equals 0, with roots plus and minus I. Complex, not real. Rotations live in the complex world. Your turn. Here is a fresh matrix C. Pause the video right now and try to find its eigenvalues yourself before I do. I'll wait. Here's the walkthrough. Trace is 2 plus 3, 5. Determinant is 6 minus 2, 4. So the characteristic equation is lambda squared minus 5 lambda plus 4. Factor it into lambda minus 1, lambda minus 4. The eigenvalues are 1 and 4. Add them. 5, the trace. Multiply. 4, the determinant. If you got that, you've genuinely got this. Trap 1. The zero vector. It obeys the equation for every lambda, so it's excluded by definition. An eigenvector is always non-zero. Trap 2. Dropping the identity. You subtract lambda only along the diagonal, a minus lambda I. Writing a minus lambda isn't even defined. Trap 3. Double counting. If V is an eigenvector, so is any non-zero multiple of it. They're one direction, not separate answers. So why care about all this? Because these special directions quietly run the show almost everywhere. In principal component analysis, the eigenvectors of your data's covariance are the very axes it spreads along. Google's original PageRank was nothing more than the dominant eigenvector of the entire web's link matrix. In control and dynamics, the sign of an eigenvalue decides whether a system gently settles or spirals out of control. And in engineering, eigenvalues are the natural frequencies a bridge or a wing wants to vibrate at. Get them wrong, and things resonate themselves apart. Let's lock it in. An eigenvector keeps its direction. A V equals lambda V, with V never zero. Find the eigenvalues by setting the determinant of a minus lambda I to 0. And always sanity check. Eigenvalues add to the trace and multiply to the determinant. Master those 3 lines, and eigenvalues will never surprise you again.